So good afternoon, everyone, and good evening, Mikey. It's my great pleasure to introduce Dr. Mikey Elmers, our invited speakers for today. Mikey, if I may say your name directly, so Mikey is a postdoctoral researcher at the Speech and Audio Processing Laboratory at Kyoto University in Japan, where he works on spoken dialogue systems for human-robot interaction and virtual agents. His research combined experts in speech synthesis, phonetics, and computational linguistics. Mikey earned his PhD, and this is where we met because we did our PhD at the same time. So he did his PhD in phonetics from Saarland University in 2023 under the supervision of Professor Ben Mubius and Dr. Jorgen Truvan. His doctoral work focused on both internal phonetic particles in speech synthesis. And he has made a significant contribution in the field of speech communication in general, with a lot of publication exploring how these phonetic elements influence perception and recall in synthesized speech. Before his doctoral studies, Mikey earned a master's degree in international culture and communication studies from Waseda University, if I'm saying it right, in Japan, and a bachelor degree in linguistics from University of Minnesota, USA. So, Mike, it's a really great pleasure to have you with us today. But before we begin, I would love to take a moment to introduce to you to our students. So in this language engineering lecture series at Alexandria University, we have a group of brilliant and passionate students from phonetics and linguistic departments here, and they are deeply interested in computational linguistics, speech technology, and AI-driven language applications. Currently, they are working on their graduation projects, which involve speech synthesis, natural language processing, and machine learning applications in linguistics. They are urged to learn from leading experts like yourself, especially about the cutting-edge research in spoken dialect systems and speech communication. We all are very, very excited to hear about your work and insights. And thank you for joining us and welcome to Alexandria University. With that, yeah, thank you again, really, Mikey, and the floor is yours.
Thank you very much. That was such a generous introduction. Hopefully I live up to it. Yeah, I guess I'll just go ahead and start. Yeah, I don't need to introduce myself since Omnia did such a good job. But I would like to say I am presenting this work on behalf of me and some very hardworking co-authors. So that would be Koji Inoue, Devesh Lala, Keiko Ochi, and Tatsuya Kawahara. So today I'm going to kind of give a brief introduction of what I do at this lab. Like Omnia said, I've kind of come from phonetics, speech synthesis, computational linguistics. So it is kind of a variety of things, and you kind of wear many hats in the day-to-day work of it all. So I'd like to introduce some of the robots, some of the systems we work with, some basic human-robot interaction ideas. And then I'll go ahead and walk you through one of the experiments that we did. So this one is titled The Analysis and Detection of Differences in Spoken User Behaviors Between Autonomous and Wizard of Oz Systems. So first I'd like to introduce some conversational robots. These are kind of popular in Japan. So you have Pepper on the left, Now in the center, and V-Stone on the right. Well, those are usually called Komus, but they're made by V-Stone. So, but in general, in Japan and kind of worldwide, we're starting to see a growing presence in everyday life of these conversational robots. But what we find is there's still a very large gap between conversational robots and human-like interaction, which is what a lot of people expect, especially as the robots start to look more and more human-like, as you will see. There's many areas that are difficult about human-robot interaction, but one of the important areas that's really hard is the appropriate evaluation of dialogue and being able to glean valuable insights from that to make improvements in the systems. So one of the things we've been looking at here is distinguishing between operator controlled, or what you'll hear Wizard of Oz throughout this talk, and autonomous systems. So the autonomous systems would be when the robot is completely done with a computer through the system. There's no human interaction whatsoever. What we like to do though often is we will have a operator in a separate booth, and they will speak through the robot. So it's a nice kind of comparison between the two. So one of the robots that I'll talk about today that we work with a lot is Erica. So she's an autonomous android. She has a human-like appearance and a synthesized voice. The one we work with here in Japan, we mostly just work with Japanese. Occasionally we'll work with English, but yeah, mostly Japanese. And especially since she looks humanoid, the goal is to replicate human-like communication skills with her. Um, like I mentioned earlier, as they start to look more humanoid, people start to have higher expectations of them. Erica can generate a variety of different linguistic phenomena, such as backchannels, fillers, or laughter. And I'll address these a little bit more in detail later. Erica also can produce some visual cues. So she has facial expressions, synchronized lip movements as she speaks, blinking and nodding. So I'd like to just play a little clip. This isn't from our lab, and this is in English, so hopefully it'll be a little bit easier. But yes, go ahead and I'll play a little bit of this.
Hello, my name is Erica. The Guardian released a documentary about me, and it seems that many of their viewers have questions for me. So, I would like to try to answer some of your questions in this video.
Okay, the first question comes from Mark from Australia, who wants to know, do you believe that your own identity is constructed from your memories?
Well, Mark, that's a really good question. My long-term memory system is still under development. At the moment, I'm able to remember people's faces and recall what we have talked about in the past. But my personality is currently designed by my creators, so it does not come from experiential memories.
Okay, hopefully that gives a little bit of the idea. So what you saw there is she's able to turn her head, she's able to look, she's able to blink. A lot of ways she can show attentiveness, which will be a theme we kind of talk about throughout this presentation as well. So we look at multiple roles because when you have a conversational system or a dialogue agent, you have to think about how are we going to evaluate what type of scenarios would we like to conduct. So one of the areas we look at is attentive listening. And this would be where the robot doesn't speak too much of its own volition. The goal is to get the user to talk a lot and just to continue to incentivize them to keep talking. Another example would be job interviews. So this can be for practice job placement. And another example we look at is as a lab guide, any kind of introduction for people who are new or showing them around. So the research question that we're going to address today is how do users' spoken behaviors, so that's how the user speaks with the machine, differ when they're acting with the Wizard of Oz scenario, so when there's a human speaking through the robot versus the autonomous system. So we plan to evaluate the system based on these user behaviors with the goal of allowing us to find areas of weakness or areas to improve for future systems. So I'm going to introduce those scenarios that we're going to focus on today in a little bit more depth now. So first is attentive listening. This is the scenario where the system listens to the user. There's been some research that shows it's very helpful for companionship, either with elderly people or in psychiatric daycares. Predominantly what they do is they will backchannel. So as an example in English. They'll ask you follow-up questions or sometimes generate empathetic responses based on the condition. And like I said, the goal here is really just to continue to incentivize the user to keep speaking. So for the examples we looked at, they were all about 5 to 8 minutes in length. And the ones we conducted in our lab involved a variety of different topics where the user might talk about food, travel. There was a category for the difficulties of the pandemic as well. So I'm going to show you two examples of attentive listening right now. So one will be autonomous. This is just with the system. And then I will show you the Wizard of Oz in the second with an operator.
アメリカのニューヨーク行った時も、食事の値段がすごく安いんです。
どんな食事ですか？
朝は、コーヒーとアップルデニッシュはよう思い出したわ。
Great. And there you can see she asked a follow-up question. She used back channels to show she was listening and to continue to incentivize the speaker. So here, this is the example with the was, so with the operator. You can see the operator in the bottom right-hand corner. They were in a soundproof booth in a different area, and the participants did not know whether or not they were interacting with a WAS scenario or the system.
子供も大人もみんな好きやから、たくさん食べて、それがすごい楽しみなんです。
素敵ですね。
はい。ちらし寿司もあるんですけどね。
Okay, great. So I think you're starting to get a little bit of the impression here between the system fundamentally, versus the operator. And the goal here is to see people in a questionnaire can often form their own opinions on what they just experienced. But we want to see if the experience itself has implicit changes in how they react. Do they speak more naturally in one condition versus another? For example. Okay, so the other scenario we looked at was job interviews. So this is where the system practices with the user as the interviewee, and the system acts as an interviewer. Most of our examples were done with students as the user or as the interviewee. One of the goals in conducting job interviews, like mock job interviews or practice ones, is it can really help because they can be very challenging. There's a lot of studies that talk about it can cause a lot of anxiety and stress. So the idea is if you have a system that can replicate a job interview scenario, that maybe you can help people prepare and then mitigate some of these performance-related anxieties. So I'm only going to show you one example for this one, just for time's sake. But yes, this will be, let me show you first.
まずは志望動機を教えてください。
はい、あらゆる人に影響を与えたいと考えてマスコミ業界を志望しました。
Great. And that was the autonomous one. I know there's a picture of a person in the bottom right-hand corner, but that was not an operator. So, but just an idea is what you can see what the scenario is like. So now I've introduced the two scenarios we're going to be focusing on in this work. So the attentive listening and then also the job interview. Now I'd like to introduce some of the spoken behaviors that we are evaluating for the users. So one of them is fillers. So this would be like and in English. Examples would be ano and eto in Japanese. They have different functions such as turn taking, floor maintenance. In some languages too, they can be used for sociolinguistic identifiers. The next one we evaluate is back channels. This is what you heard a lot in those examples. So that would be hi in Japanese or in English. Back channels can convey attentiveness, interest, understanding, acknowledgement, but very importantly, they don't signal to the speaker that you are trying to take the conversational floor. And then, just as a side note, there's been research into the frequency of back channels for different languages, and we find that Japanese has back channeling much more frequently than American English. So we also looked at disfluencies. So this is a much more catch-all term. and it can include many phenomena such as lengthening, truncation, repair, and word fragmentation. The research is a bit mixed on whether or not disfluencies are a net positive or negative. So there is some work that shows that a material that is present after a disfluency is better remembered. But conversely, many people, if you've done any kind of public speaking, know that disfluencies are often carry negative implications, making you seem less prepared, less knowledgeable, etc. And then lastly, we looked at laughter. Laughter can foster social relationships. It can contribute to engagement, understanding, and reasoning. Specifically, there's been work that's shown in a job interview scenario that laughter between the interviewer and interviewee can lead to an increased likelihood of a job offer, a stronger connection, and then that certainly rapport building as well. Okay, so those are some of the spoken behaviors we will be looking at. I would like to walk through the methods now. So our participants interacted with Erica, the humanoid android robot we introduced earlier. All of the interviews and dialogues were in Japanese. We only looked at the user's spoken material. So that means we did not evaluate the system's responses at all. Like I said earlier, with the attentive listening, it's more follow-up questions and back channeling. But with the job interview, it was actually more structured with them, leading the interview. But none of those responses were evaluated here. The two scenarios were the attentive listening and the job interview. And then we looked at it for two conditions, that is the autonomous and the Wizard of Oz condition. So we did both descriptive and inferential statistics. So we compared the differences between the WOZ and autonomous system. For segmentation, we used interpausal units or IPUs. And what this means is whenever we, during the speech, encountered a pause of 200 milliseconds or greater, there was a cut and was segmented into a new IPU. For the linguistic annotations, we looked at both count and the number per second for the fillers, backchannels, disfluencies, and laughter. We did do text tokenization as well, and from that we got the length, which was just the number of tokenized characters per each IPU. And then we also got speaking rate, so the length divided by the duration. So we did predictive modeling here. And the goal was to determine, based on these features, if we could predict whether the user was interacting with the WOZ or autonomous system. So this was a binary classification task, with the input being the linguistic features and what I'll introduce in a second, some acoustic features as well. And then the output is whether or not it's WOZ or autonomous condition prediction. So we had a few models. We had a baseline, which was just a very naive, simple predict majority class for all instances. We also looked at logistic regression, support vector machine, random forest. Here, and you'll see when I talk about it a little bit more later, the goal wasn't to necessarily do any kind of cutting edge modeling here, but just get simple, interpretable predictions. And then the metrics we used were accuracy, precision, recall, F1 score. So here I'll go over the modeling information and then the follow-up ablation study we did. So for the linguistic features, or for the modeling information, we had the linguistic features that I mentioned. Then we also had 4 acoustic features, so the mean and standard deviation for both F0 and for power. Each of these were calculated per each IPU, so for each segment. We had random sampling for reproducibility. We had random sampling and then the preset seed for reproducibility. We did an 80-20 training test split. And importantly, we made sure to allocate all of a user's IPUs entirely to just the training or just the test set so that there was no form of speaker identification occurring. Like I said, here we were just trying to see areas for improvement. So we didn't do any kind of hyperparameter tuning and just no fine tuning in general. After we had the model, we conducted permutation-based variable importance analysis. And what this does is it quantifies the significance of each feature. And higher scores indicate a larger effect on the model. And we did this on the random forest model for both attentive listening and the job interview scenario. So for the results, there's two big takeaways I want to talk about with this slide. So on the top, you will see just the feature counts for the attentive listening, and on the bottom, the feature counts for the job interview. So when it says here 26.88% fillers autonomous, that would mean 26.88% of IPUs for the autonomous condition in the attentive listening scenario had fillers in them. So the two takeaways I want to point out here is that there were significant differences between the autonomous system and the WAS system for each respective scenario for all conditions except for disfluencies. The other thing I want to point out is that if you look, you'll notice that sometimes trends that you find in the attentive listening scenario are not present in the job interview scenario. So for example, you find that there are more fillers in the WAS condition for attentive listening, whereas you find less fillers in the job interview condition compared to the autonomous system. And so let me give you an example of each of these. So for the attentive listening system, you might generate fillers naturally because it's user-generated speech. The system is really only there to keep you talking, so you're going to have to use a lot of mental resources to keep talking, which would probably lead to more fillers. Conversely, in a job interview scenario, you are trying to put on a special type of speech where you seem very competent, high performance. You want to present yourself very well to the interviewer. So you would probably actually want to reduce your fillers and make sure you had as few as possible. So, and you find that here with the job interview scenario, there was a lot less fillers in the WAS condition than there was in the autonomous, indicating that maybe having a human behind the microphone did a better job of making it feel like a legitimate interview scenario. But yes, I won't go into examples like this for all of them, but there's examples for most of the features that you can see that there is differences between the two systems, indicating that the autonomous systems don't necessarily meet the same level as the operator-driven ones. But also that just because you find a trend in one direction doesn't necessarily mean it's applicable to other scenarios. A lot of these trends are scenario dependent. On this slide, so we have the other features. So before these were the counts on the last slide. On this one, it would be the feature per second as well as length and speaking rate. I won't go into all the details here, but similarly, the two same points are apparent from these results as well, which is that in almost all cases for each respective scenario, you find significant differences between the autonomous and the operator system, with, again, the exception being disfluencies, but in this case, disfluencies per second. And then again, you find that there will be different reasons based on the scenario why you might see one value being higher than it would be in a different scenario. I'm not going to go into the detail of these examples. If you guys have questions, please feel free and I can come back. I will say that the number in parentheses is the standard deviation though, and the number outside the parentheses is the mean. Okay, so for the modeling, like I mentioned earlier, we had a baseline majority. So that's why you'll see that the recall is just 1. And then we have the LG, which is logistic regression, the SVM for support vector machine, and then random forest is RF. And you can see that for each of them, there's a model that performs better than the baseline, but it's quite a minor improvement. Like I said here, the modeling wasn't the goal. I'm sure there would have been ways to adjust the hyperparameters or look at other machine learning models that would have improved it. But the goal was just to get a general idea. This is where I want to draw more of the attention to is which features contributed most. So initially when going into this, I was hoping that it would be primarily linguistic features. When you look at this, on the left-hand column, you can see the feature list. In the middle, you'll see attentive listening, and that'll be ordered highest to lowest. And then on the right, you'll have job interview, which isn't always highest to lowest because it's based on the attentive listening column. So bear with that. But ideally, I was hoping, based on just looking at the different linguistic behaviors of the user, we might be able to get a really good idea of whether or not they're interacting with what type of system. Unfortunately, that didn't really seem to be the case. The primary driver for both models was the acoustic features, as you can see. We did look at a couple models. At the bottom, you can see we had an acoustic plus linguistic model, an acoustic only model, and then a linguistic only model. And what we found was the acoustic only model performed slightly worse than the acoustic plus linguistic model, but the linguistic only model performed quite low. And as you can see, for some of them, these values aren't absolute, by the way, for variable importance for this type of modeling. It's all relative, so don't worry about that. Just compare that to what you find in the column. But what you'll see is, yes, the acoustic features can be much higher, sometimes double or way more. Some of those features at the bottom are basically around or at 0. So the linguistic features can be a little bit of a bump. Like I said, the acoustic plus linguistic model did perform slightly better, but alone, they are not able to detect whether the user was speaking with a physical person or just with the system. Okay, so I'd like to start to wrap up, summarize some of the ideas. So first of all, there is a number of caveats. The data collection for this was actually done over many, many years, 5 to 7 years. As I mentioned earlier, there's some big topic differences, especially in the attentive listening scenario. That would be things like when I mentioned travel, food, or the difficulties of the pandemic. Those can have very different effects on how the user speaks about these scenarios. The immediate context was all we evaluated, as I mentioned, since we considered IPUs, meaning we did not evaluate over the entire dialogue. Additionally, there could be multimodal cues, such as facial cues, other physical cues, gestures, etc. None of those were evaluated here, and we also did not evaluate any age or gender-related effects. To summarize, so what we looked at here is human-robot interactions. And because we had recorded many scenarios over many years, we wanted to see if we could parse that and see what users' behaviors changed based on the different scenarios, and if it could give us ideas on areas to improve the system to hopefully close the gap between the autonomous system and the WAS. So we looked at feature differences for WAS and autonomous conditions for both attentive listening and job interview scenarios. What we found is that we were able to surpass the baseline for accuracy and precision in some cases, and some models surpassed for the baseline for F1 as well, but they were minor improvements. And then lastly, with the permutation analysis, we were able to show that the acoustic features were the highest contributors and that the acoustic plus linguistic model performed best, better than just the acoustic model or the linguistic only model. So kind of the big takeaways for today is the user's behavior differs between the system and an operator. And like I said, the user has no way of knowing. We don't communicate this to them. Essentially, and this may be discussed later, there is a speech synthesis aspect, that is another important caveat, that when you have a operator, we're not using that in most cases. In some cases, we do take what they say and put it through some kind of modulator so that it sounds like speech synthesis for a better comparison. But there's other times where we've just compared it just through the voice. But the speech synthesis quality is actually pretty good, and it's usually when people do the post interview surveys is not really a criticism. It's usually things like turn taking or other things about the robot. So I guess what I want to say here is that the user is able to feel something different in the way that a operator speaks than what the system is able to do linguistically, and it makes them able to express themselves in different ways. An example I like to think, or I use sometimes that I think maybe helps with this, with the imagery is, everyone here speaks clearly multiple languages. Usually when you meet someone who is a non-native in your first language, you can kind of tell, and often you will modulate, whether it's the speed, the level of your vocabulary, etc. You know, you can almost instantly detect what skill threshold they're at and modulate yourself to accommodate to them. And I think there's something similar here, but instead of accommodating, they're kind of detecting the upper skill level of the robot, and they bring themselves to essentially that level. So there is still a large gap between the autonomous system and human-like interaction, and we are working on trying to fill that gap in many different ways. That's an area that I'm more than happy to discuss during the Q&A. Importantly, it's very necessary that we continue to look at different methods to evaluate user behaviors. Like I said, this was one method. Sometimes we do user surveys. There's many other different methods. There's a workload task to kind of measure how cognitively difficult a scenario is. These are just a couple examples, but there's many more, and I think it's very important to not only improve these systems, but also think about how we evaluate the system so that we can make sure the improvement is actually doing what we'd like. So here's a list of my references. With that, I guess I open up the floor to questions. Thank you.